Okay, this is lecture 11 on invariant maximality reversal, part number 9. Please.
Thanks. Okay, so today we're really finishing the reversal. Um, we're talking about the introductory sections that are preliminary to really starting the reversal, which was last time. Section 4.3 really starts it. Uh, there's been some important expositional advance, which I will make clear here that I think is I'm happy with. Um, okay, so the text of the previous lecture 10 is at the downloadable lecture notes page, and that was on 4.3, and the official version of section 4.3 in full is on my downloadable manuscript page, or a polished version. Um, and of course, the statement we're reversing has been constant, which is important. Uh, Reversing a statement that changes during the reversal is not a good idea. We try to avoid that. All right, so notice we have the same table of contents except for this. I have changed the table of contents. Remember, that was the bookkeeping section. I called it sections 4.3 to 4.5 justified, and it was always a mysterious section that we never covered. Now it's going to be less mysterious, uh, and you'll see that everything's been streamlined. So I'm going to describe that. All right. So we're going, note there's been a change in the title of section 4.6. Uh, and what happened is I've isolated the key result about the order invariant graph that's used throughout sections 4.3 to 4.5. And that key information is a simple one to state, and it's now put in section 4.2. In other words, today we're going to talk about that key thing. And then section 4.6 merely has to present the formal definition of the graph, the formal definition of the graph, which you know that I don't want to put early in because it's just a mess. It's a lot of clauses, you see. Um, and then section 4.2 today talks about the framework for defining the graph without giving the actual clauses. Without giving the actual clauses, defines the actual graph, the framework for defining it, and then derives actually from the framework, you can derive this basic fact that's been moved from 4.6 to 4.2 that's used in order to make use of the graph. All right. So before starting with section 4.1, which is even more preliminary, no, 4.1 is notation, some presentation of finite languages. We give a strategic overview of the entire reversal from a certain useful perspective. We do this first because we already covered sections 4.3 to 4.11, with the exception of the bookkeeping section 4.6. So we can do this first and you can make sense of it because you can see from what we did earlier um, uh, that this is a strategic overview. So the strategic overview involves three elements. Three elements. One is indiscernibles. These assert that just like in regular model theory, and set theory. This and everything else in logic. This asserts that truth values of statements about objects don't change under various rearrangements of the objects. And representation. This represents defined sets atomically or existentially. This develops into separation in set theory. So the extreme form of representation is any first order statement. It will be in set theory, be any first order statement about elements of a given set can be represented by the elements of some particular set. That's called separation. So representation is kind of preliminary to that. Representation has some sets that are defined somewhere can be represented in some particular way. You know, it's much more general representation, but it develops into separation in set theory. And tupling, this represents the finitely many points by a single point. You can represent finitely externally finite. This is externally finitely many points by a single point. Maybe I should actually, because this is all in the context of non-omega models. This usually just follows from pairs that you can represent 2 points by a single point, but not here it's a little more delicate. It doesn't really quite follow from that in a certain way, in a certain sense, because we're going to have we're going to be doing some restricted tupling. In this manuscript, we have some restricted tupling where the coding is not 1-1 always. Any two tuples with the same max, I'll just say it now, and we've seen it. We've seen it before. Any two tuples with the same max have only one code. Uh, Not any two tuples have only one code. You might have the same code for different maxes. Uh, yeah. Okay. All right. But anyways, uh, and different lengths also. Yeah. Lengths and maxes. All right. Um, so these components are familiar throughout mathematical logic. We now view the reversal in terms of ever strengthening 1, 2, and 3 as we go from the end of sections 4.1 through the end of section 4.11. The end of section 4.2 is taken to be simply the statement being reversed. The statement being reversed. G is the order invariant graph we work with, and S is the maximal clique. So at the end of section 4.2, we have G and S. Just as, that's preliminary to starting the reversal in 4.3. All right, in section 4.1, we don't have anything. We have just notation. We have basic infrastructure, including presentations of the syntax and semantics of the three finite languages that we use, and enumerations of formulas. There's not much in section 4.1, except just some the crudest preliminaries. Section 2 is more preliminaries, but it's more meaty, and it ends with what we would call the atomic indiscernibility of these numbers with negative parameters. Uh, and that's just from the invariance. See, the only thing we have in section 4.2 is the statement we're reversing. We don't do anything with the statement we're reversing until section 4.3. So we have atomic indiscernibility of this with negative parameters. That's what the statement says. And then S is, so I want to say there's really not much representation here, except so I'm sucking out what is in the statement being reversed. It has a certain indiscernibility in it, right? And because it says that something's invariant, right? And it also has a kind of representation, namely that I can represent S itself. It's just a representation of S. S itself is the set of points where you're still a clique when you add it on. That just means that since S is a clique, that just means S is a maximal clique. It just means S is a maximal clique. Yeah. Um, I'm sorry. Yeah, S is the set of all things such that you can do this. Yeah. Yeah. Um, okay. So there's no tupling at all just from the statement. And based only on the statement reverse, framework for defining order invariant graphs. So this section 4.2, which we're going to cover today, has some indiscernibility and some representation. Okay. Any two elements of S, um, I guess any two elements of S, if S is, I guess if S has any element, then S is, if S has any element, then S is a clique. Okay, so it looks like, maybe I should say this. It looks like this equation actually is equivalent to saying, is actually outright equivalent to saying that X is a maximal clique. Yeah, it looks like that this is nice. Unless I'm screwing up here, this statement, this equation, this representation is equivalent to saying that S is a maximal clique. I guess that's right. Okay. All right. Anyways, yeah, so this is a very nice situation. Yeah. Okay, now section 4.3, which we did, we did everything 4.3 to 4.11. All right. We this language is already described in section 4.1, this finite language, and we have this indiscernibility for these numbers with lower negative parameters. And this has quantifiers in it. So there's something interesting here. And then we also have representation of properties of negative numbers defined in here. This is in these languages by atomic formulas, right? I think the indiscernibility with respect to the other languages follows from this. So uh, we have indiscernibility actually with respect to all three languages here. Yeah, I should say that. Yeah, we have. I'll fix this happens because this is a laptop which is very touch sensitive. Don't worry about this. In fact, let's fix it now. Oh, I'm not in. Yeah, just a second. Just a second. Yeah. Okay, that's what we had. That's what we did in section 4.3. All right. Now, in section 4.4, the negative reduction section, um, uh, yeah, I don't know if I want to bother saying this. We just have this indiscernibility. The whole point is we don't really care. Yeah, at some point we don't. These auxiliary languages are only used to help us do this. So I'm not going to repeat this, but already here we're not finished because in 4.4 I heavily use these languages. But at the end, I only care about this language. I only care about this language at the end. This is the one with quantifiers. These don't. And I've already screwed up here a little bit. These are the quantifier frame. I'm sorry. I'm sorry, these are the quantifier free languages. These are the quantifier free ones. Come on, come on. Get my act together here. Let's. Okay, there we are. Okay, here in section 4.4, we have better indiscernibility. We have the same indiscernibility, but for more numbers. We have indiscernibility with respect to some negative numbers, remember, whose soup is 0. Uh, it's always with parameters that are below the indiscernibles used. Okay, you don't understand what I'm saying. Properties of negative, yeah, with lower negative parameters. Representation of properties of negative numbers defined in here. Okay. Representation also is preserved. Okay, so that's what 4.4 does. And then 4.5 is no different, is exactly the same thing, except the representation of properties of negative numbers in this language uses only 5 parameters, 5 instead of many. We spent that whole section cutting this down to 5. That's why that section is called tupling. And the tupling is weak. It's restricted tupling. If 2 tuples have the same code and the same max, maybe I have to say same code, same max, same length. I think. Yeah. Double check that. Yeah. Okay, same length and same max. Then they're equal. Yeah. See, so that's a restricted kind of tupling. So, so in other words, it's just not a matter of how how I handle pairs, I think. I think you have to say more here. Um, it's important that this be external. Yeah. Okay. This is the so-called bookkeeping section, which really now is the full definition of the order grand graph in all its glory. Full definition. It's defined in 25 clauses. All right. Then we have, in the next section, we have we move we're moving. I want to say this. Yeah. We've moved to here. If you remember, we moved there. Um, okay. The next section, we don't do anything, we don't change anything, but we get definable internal pre-well orderings. We developed definable internal pre-well orderings, which are going to become, so to speak, our ordinals later. And then section 4.9, we actually have a second order structure, weak second order. With definable indiscernibility, full-blown indiscernibility. It's always limited. When I say definable, there's going to be bounded quantifiers somewhere high up. Okay, definable indiscernibility with lower parameters. So, and representation of definable sets by atomic formulas and tupling of finite tuples by points. Um, I might as well say this is really separation. Yeah. And then we redo 4.9. We cut 4.9 down. So the step from 4.9 to 410 is Gödel's monograph on L. That's what that step is. So we developed this with an appropriate form of V equals L. If you remember, I don't know if you remember those dollar signs and double dollar signs. That's the level in the constructible hierarchy. Yeah. Then we convert to the language of set theory and derive the existence of large cardinals in initial segments, um, in large cardinals with initial segments. And we derive the existence of large cardinals in initial segments. We derive this existence using the indiscernibles and the separation, unrestricted representation. Which is the same as the unrestricted separation representation. Okay, just let me go over this again because I made all these changes, just expositional. So we start off with no indiscernibles, no representation, no tupling, basic infrastructure, set up the languages and enumeration of formulas. In section 4.2, we note that the statement we're reversing has atomic indiscernibility in it and has the representation of S in it. just the invariant maximal clique that's existentially instantiated from the statement. It's represented by this equation. Uh, we have no tupling. Um, and this is based only on the statement being reversed. So this is all preliminary stuff. 4.3, we did last time. We have the indiscernibility with respect to all these languages, and representation of properties of negative numbers defined this way by atomic formulas. That's the atomic representation section. That's what 4.3 is. The next, the indiscernibility is strengthened to have infinitely many indiscernibles with actually finally many on top. So the order type of these indiscernibles is omega plus K12 plus 1 with lower negative parameters and representation of properties of negative numbers. In other words, all this representation stuff that I did up here is lifted here. Atomic representation. Atomic representation done also in the negative part. There's no tupling, and the R's are strictly increasing negative numbers with sub zero. Then the next section, this is very bad, having all these parameters. In the next section, we keep the same indiscernibility, but now the same representation, all that's the same. But and we also now have what's new is we have restricted tupling of externally finite many points by single points. And because of that combined, we actually get we can use only 5 parameters. It's all mixed in that you can do that plus restricted tupling. 4.6 now is simply the full definition of the ordered invariant graph, following the rules and frameworks set up in section 4.2. Then we have much stronger same kind of indiscernibility now for the numbers 1, 2, 3, ... with low parameters. That's not really a change because we just move from -1, 1 to 0, infinity. And representation of sets defined by L of K by atomic formulas. So now the representation actually is with respect to the full language, not just the finite language, the full language. Atomic representation using the full language. Actually, it's existential. This is not quite representation by atomic formulas. It's actually we back off a little bit. It's in order to get it defined by all the formulas. It's an existential thing with 7 parameters, but it's quite controlled. That where we represent the sets. And then we have restricted tupling for we have the same restricted tupling that we had here. And this all comes from moving from -1, 1 to Q0 infinity. Then we have the same thing as here, except that we have we develop the definable internal pre-well orderings. We have to actually make sense of what a pre-well ordering is and prove they're comparable and all that junk. And we also have restricted tupling with finitely many externally. Yeah, the same in tupling. All right, now we go to a weak second order structure with definable indiscernibility with lower parameters and representation of definable sets by atomic formulas. The full-blown thing I think I still want. No, I think this gets better. I think this gets better. Right. Yeah, because we define this structure properly. This gets better. It's actually a separate representation by atomic formulas, very close to separation. And then we have tupling as before. And then we actually go push everything. Oh, no. Then we have to redo this. We have to develop constructability in this framework here before we do actual set theory. We have to talk about constructability in here and say we can do that. And then finally, we convert everything to the language of set theory, and representation becomes separation. Representation. Separation. Yeah, all right. I won't say anything more about this. Derivation of the existence of large cardinals in initial segments. That's done using the indiscernibles and the separation. That's done using the indiscernible, the separation. And the how do I say this? And the and the V equals L. Yeah. All right. So this needs a little bit of perfection to give this overview. I think this overview is useful. Now that I made more changes, now I'll go through real quick. Section 1, we don't have anything. We just develop notation and the three finite languages. In 2, we have atomic indiscernibles with negative parameters and negative parameters below. Yeah, they're automatically below the indiscernibles used, of course. Yeah. And then we have atomic representation. No, we have representation only with respect to S because we're only using the original statement. We have no tupling. Uh, then we have atomic indiscernibility. Uh, no, we have language indiscernibility. These finite language indiscernibility with lower negative parameters. We have representation of properties of negative numbers that are defined these languages by atomic formulas with many parameters, no tupling. We have indiscernibility extended to infinitely many indiscernibles with of order type omega plus. I'm sorry here. Whoops. With K12 plus 1 indiscernibles with lower negative parameters. Representation of properties of negative numbers defined in this language. This is the only language we really ultimately care about. These other ones were for auxiliary languages to help us. Yeah, by atomic formulas with many parameters, no tupling, and ours are strictly increasing with sup 0. We have indiscernibility, again, the same indiscernibility. Now the representation is not with many parameters, but with 5 parameters only, and we have some serious tupling. Now we never had tupling before. Tupling of externally finitely many points by single points. If 2 tuples have the same code, same length, and the same max, they're equal. Then we have bookkeeping. We have finally the definition of the graph. Then we have the indiscernibility of the numbers 1, 2, 3, dot, 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 but that's nothing because we just moved from here to here. Representation. Oh, but the indiscernibility is with respect to lower parameters, not just negative ones. Where did that come in? That came in up here. That important move was in here. With lower negative parameters, yeah, but lower negative parameters, lower than the negative indiscernibles used. Lower than the negative indiscernibles used. Yeah, that's an important point. See, these indiscernibles are really the strong, good kind, not these weaker kinds that we've been talking about when we just had positive indiscernibles. So this is lower than the negative indiscernibles used. This is important. Indiscernible with parameters lower than the indiscernibles used. This is important. Important point. Lower than the indiscernibles used. Very important. Okay. And that's what you have in set theory and in SRP type cardinals. Representation of sets defined by, okay. Okay. This is the same, except all we did is develop these pre well orderings so we can develop ordinals. Then we go to a weak second order structure with definable indiscernibility with lower parameters, with parameters lower than the indiscernibles used. Representation of definable sets by atomic formulas. To tupling of finitely many points by points, unrestricted, now unrestricted. Yeah. And then we have the same thing, except with an appropriate form of V equals L. We have to do this kind of thing is a Gödel monograph thing from 4.9 to 4.10. And then section 4.11, we convert everything to the language of set theory. Representation becomes separation, derivation of the existence of large cardinals in initial segments, derivation of this existence using the indiscernibles and the separation and the V equals L, unrestricted, and the V equals L. Well, we can get rid of that. By now we know it's separation. Yeah. Okay. All right. I'm not going to go through this again. All right. I polished it. I did many polishings of this overview before I even came here. So this is the 10th polishing. All right. Now, the introduction 4.1 looks like this. We're reversing this statement, and I'm not going to spending much time here. You know what order equivalence is by now, order equivalence of tuples and order invariance of a set. Okay. And then we have F invariance, where F is a partial function. F invariance, where we talked about this, F invariance, clear what this is. And then we have yeah, my notation for a function of the kind we want. This thing here, we're still talking about the statement that we're reversing. That function is this. Okay, right? And then we're talking about invariance with respect to that function. And then here's the graph theory we use. The simple graphs. There are no loops, and all the edges are undirected. So I actually make it a relation. It's an irreflexive symmetric relation. This relation is irreflexive because we have no loops, right? Okay. And the word adjacent just means that it's the edge relation. Okay. And then ordered variance. If I have a graph is ordered invariant if the adjacency relation is an ordered invariant subset of twice the dimension of the vertex set. Okay. And then these definitions support the statement we're reversing. All right. Now, the whole reversal starts with fixing a big number. The square brackets 3 means three twos with an exponent with k on top, exponential stack, right? And we define a particular order invariant graph, and we let S be any maximal clique in G, which is also invariant. Okay. And the quantity K plays more or less a role. Yeah, at some point we already yeah, I think I should say it here. We go to K12, not just K. Well, no, we're showing, okay, I shouldn't have done this. Yeah, okay, just 1 second. Be nicer about this. Yeah, we're starting with this statement. We start by fixing K, defining a particular order. Yeah, no, this is fine. And then we use the dimension K12, and we let S be in dimension K12. And we also, which is also, now here's where I made a mistake here. Okay, the fixed quantity K plays less and less of a role until finally at theorem 10.2 we entirely remove K. So using that K has been arbitrarily chosen up to then. Now, given the logical structure of this, I want to make it clearer. We make the following inference. Theorem 10.1 implies theorem 10.2, where theorem 10.1 is just reflecting on the entire 4.1 through 4.9. Okay, now this is 4.10. Yeah, chapter 4. Um, sorry here. Yeah, okay. Where theorem 4.10.1 is by reflecting on the entire development, 4.1 through 4.9, based on our big number K. The above application is proved itself using the compactness theorem for predicate calculus. So we fix K, we do a lot of work. Then we say, hey, by the way, for all K blah, because because K was arbitrary. For all K blah, for all K big enough, for all K big enough here, blah. And then we say, okay, compactness, we can get rid of the K. That because the K becomes internal in there. Okay, so we can do that. Now, we let J be this function, and we let D be the domain of J. D is actually this. This is important. This is this set here. Okay, now we restate the thing we're reversing as every order invariant graph has a J invariant maximal clique. That's the statement we're reversing. That's the right form of it. We don't have to, that's the best form of it, to say it that way. We're still in this preliminary section. L of R is just the usual predicate calculus with not or, and there exists with infinitely many variables a binary relation less than, and the R area relation RR. We will not need equals. We won't need equals. And for the semantics of this language, we use these structures where RR is anything. And we optionally use so the semantics is all clear, just Tarski's definition, but we also use a parameter Q for limiting the quantifiers. So you can see here, this doesn't do anything yet. This doesn't do anything yet because we're still in the atomic formula case. This doesn't do anything with the connectives. This doesn't do anything with, doesn't have any effect with the disjunction case, but with the existential quantifier case, it kicks in here. There exists P less than Q. Okay. All right. So this now we have these fragments. So this is just the atomic formulas with M variables and with arity R for the relation. And then what's the recursion on the first term? The recursion is I plus one. It's all the ones with I, closing under negation, disjunction, and existential quantification. And then when we put a zero underneath, we just mean that we want to have the quantifier free part. So N is the logical complexity. So here we are. N is the logical complexity. M is the number of variables. R is the arity of the relation symbol. And the semantics is given the same way, except that the assignments are the assignments are Q minus one, are from Q minus 1 to the M, because the variables are only V1 through VM. And we really only have these three languages I keep talking about. When we use this, we always use the less than Q semantics. When we use these, we always use the semantics without the less than Q, because less than Q only kicks in with quantifiers, and these don't have any quantifiers. And the relation symbols that are used are R super K, R super K4, and R super K8, respectively. And we let T of K be the number of formulas. Whoops. That doesn't belong there. It's just the number of formulas in the language. And then we need an estimate. We need an estimate on the cardinality of these things. And the only thing that we care about, I mean, I actually do this in gory detail, these rough estimates. But the only thing we care about is the number of formulas in the first language is K4 over 256. The number of formulas in the second language is this, and the third language is this. And we define the enumerations in some intelligible way. We want to enumerate all the formulas. And uh, I just talk about how you first do it with quantifier complexity and then with the number of letters in the formula, and then the lexicographically through the listing of the 13 letters. Okay. I mean, you don't have to do it quite that way. But here's the point. In the enumerations, and this we used in section 4.3, the atomic formulas appear first. Every not A appears after, every not alpha appears after alpha, every alpha or beta appears after alpha, beta, and every there exists VIA appears after alpha, alpha because it appears after alpha. Okay. Now, that's section 4.1. 4.2 is more interesting. And this is the framework for a presentation of the graph. We have declared blockers, and the graph. Declared sets, declared blockers, and the graph, G. We define adjacency by X and Y are adjacent if and only if X and Y are distinct, and X does not block Y, and Y does not block X. We put a number of stipulations on the declared sets, declared blockers, and blockers so that we'll be adhering to. And theorems 421 to 424 and 426 are actually consequences of the definition and the stipulations. So we're doing this without actually giving the graph in its gory detail, which is done in section 4.6. The first stipulation is the declared sets. So the declared sets are the things that can get blocked, are the basic things that can get blocked. Other things can get blocked because of order equivalence. You'll see what I'm talking about in a second. The declared sets are non-empty pairwise disjoint sets. No element of one declared set is order equivalent to any element of any other. These are completely separate. If X is the declared blocker of Y, then Y lies in some declared set. And X and Y are tuples of the right kind. If X is the declared blocker of Y, and XY and X prime Y are order equivalent, then X prime is the declared blocker of Y. So I'm saying that the declared blockers of Y form a relatively order invariant set, order invariant relative to Y. See? Okay. Remember, the whole graph is essential that it be order invariant. All right. If X is a declared blocker, then max X is less than or equal to max Y. We're going to have this. We're going to adhere to this. X is not a declared blocker of X. So we'll later add stipulations that require that certain declared blockers X of certain Y have max X less than max Y. That's going to turn out to be very important. In other words, most of the time, this is going to hold, but not always. All right. So we now define X blocks Y if there's an X prime, Y prime, such that X prime is a declared blocker of Y prime, and XY and X prime, Y prime are order equivalent. So the blocker relation is the closure of the declared blocker relation under order equivalence. This is important. So the declared blockers are kind of the immediate stuff that you care about. And then you have the blocker relation that comes out of that by closing it under order equivalence, because remember, the graph has to be order invariant. Okay? All right, and X and Y are adjacent if and only if X and Y are different, and X does not block Y and Y does not block X. All right, this is clear. So now we have defined the graph from the declared blocker relation. Okay, and X and Y are adjacent can be thought of as having two parts, X not blocking Y and Y not blocking X. The first involves max X less than or equal to max Y, and the second involves max X greater than or equal to max Y. Mostly, we have max X less than max Y or max Y less than max X, but not always. The blocking relation, I mean, and in other words, I'm saying that we could have X blocks Y and Y blocks X. This sometimes happens, but most of the time that just does not happen. Most of the time we want to know that that does not happen. Okay. All right. The blocking relation X block Y is ordered invariant irreflexive. The adjacency relation is ordered invariant irreflexive and symmetric. Uh, the adjacent relation is symmetric. Yeah. Let X be in some declared set. Y blocks X if and only if Y is a declared block. Okay, so blocking is the same as declared blocking. If you're in if the thing being blocked is in a declared set, right? Then the notions are the same, declared and being and blocking. All right. The blocking relation isn't the same as the declared block relation, only because declared sets are not required to be order invariant. Just useful. The declared sets are these useful things. I want to really understand who blocks them. All right. G is the order invariant graph with the above adjacency relation. And for the addition stipulations, we use four general categories of X, four general categories. Um, yeah, I'm going to go over some, but it's all right. We can survive me going over a little bit. Normals, abnormals, exceptionals, and strays. This is a partition. Normals is the ones we really care a lot about, and they're the ones that we use mostly. Normals mean that the maximum term is the last term. There may be other terms which are maximal, but you can't go to the extreme and make it constant. A constant tuple is not normal, right? A constant tuple is not normal, but a normal one means the last term is the largest. All right, abnormals means the first and last terms are smaller than the max. So these are very different than the normals, the abnormals. The exceptionals are when the first term is strictly bigger than all the rest. Okay, this is different than abnormal and normal because it's the first term that's bigger than all the rest. And then the strays are just none of the above. It's clear these categories are all order invariant and partitioned into four infinite classes. A normal, abnormal, exceptional set is a non-empty set consisting entirely of normal, abnormal, exceptional tuples. Strays we don't really pay much attention to, although strays can block things, but nothing blocks a stray. Nothing can block a stray because strays can't even be in these uh, sets. What did I call them? Yeah. Declared sets, sorry. Yeah. Every declared set is a normal set, an abnormal set, or the set of all exceptionals. So the set of all exceptionals is okay, is just if you get into the exceptional world where the first coordinate is bigger than all the rest of the coordinates, strictly bigger, then there's only one declared set, and uh, there's only one blocking relation. Uh, period. But the rest of them are more fluid. Except strays don't have nothing blocks strays. Strays aren't elements of any declared set. The rank of a normal, okay, now the rank of a normal X is the position of the beginning of its longest constant tail. And that could be for normals, that could range anywhere from 2 through K12. The rank of an abnormal is the number of terms which are maximum. And the possible ranks of abnormals range from 1 through K12 minus 2. And exceptionals and strays do not have ranks. Normal rank refers to ranks of normals only, and abnormal rank refers to ranks of abnormals only. Note that if two normals have different ranks, then they're not order equivalent. And if two abnormals have different ranks, then they are not order equivalent. Of course, no normal is order equivalent to any abnormal. And so in section 4.6, we track the ranks. In fact, we have the very convenient stipulation. Any element of a normal declared set has a different rank than any element of any different normal declared sets. Any element of an abnormal declared set has a different rank than any element of any different abnormal declared set. You see, all of this stuff is designed to make sure that I don't double define the graph. In other words, that my definition of the graph in section 4.6 is actually well defined. We want to make sure there are no ambiguities. You see, that's because we define the blockers differently for every one of the declared sets. Every declared set has a different kind of blocker. So you have to make sure that the declared sets don't overlap and so forth. That's what all this is about. So we have a stipulation. If X is a declared blocker of Y, we certainly want X and Y to be distinct, right? Abnormals do not block. We need to know this. Abnormals don't block. And X may be normal or exceptional or stray, though. And Y is abnormal is as normal or abnormal or exceptional to be blocked. You don't block strays. Strays don't get blocked. If X is not exceptional or Y is not exceptional, that is, we're not in the fully exceptional world, then we do have this max X less than max Y. If we have this, we do have this important. And if Y is exceptional, then we also have that X is exceptional and max X is less than or equal to max Y. Actually, max X might be equal to max Y, in fact, but X can't be equal to Y because of this. Stipulation E holds if we remove the word declared. So this actually holds for blockers, not just declared blockers. Yeah, right. You got to check that because of this is all order invariant stuff. You see. Nothing blocks itself. Abnormals don't block. Strays are not blocked. All blockers of normals and abnormals have lesser max. Every blocker of an exceptional is an exceptional with no greater max. All right, the next stipulation is the set of all exceptionals is a declared set, the unique declared sets, not normal and not abnormal. The blockers are the blockers of exceptional Y are the exceptional X, not equal to Y, which are where you either drop the max. So if you want to block an exceptional, you have to be exceptional yourself, and you must have dropped the max and kept the rest of the terms identical, or you have the same max and or you have the same max and the same max of the result, the same max and the same max of the rest of the terms. So either you drop the max, which is the first term, and keep the same rest of terms, remaining terms, or you keep the same max, which is the same as the same first term, and keep the same max of the rest. All right. And this, by the way, is the stuff that this is the stuff that drives tupling, the restricted tupling. This is the restricted tupling apparatus. See, the first term is going to be the restricted tupling of the remaining terms. That's how that works. Okay, now we have this theorem from what we said with the stipulations. If X blocks Y, then X is not abnormal. Y is not stray. X and Y are not adjacent. X is not Y, and max of X is less than or equal to max Y. If X or Y is not exceptional and X blocks Y, then the thing doing the blocking has to be smaller in max. If Y is exceptional, then all I did is repeat what I said before with more English. That had more English. This has more letters. Okay. Now, all through this chapter, we also use the star notation. X star M, now we've already explained that, but it means that you stretch the last term of X, stretch it out, repeat it so that the whole tuple becomes of length M. You can do that with this condition. And then we occasionally use something a little more complicated, X star M, Y star R. This means you stretch X to become length M, then you start all over again with Y and stretch that so it's length R, and then even this more generally. Yeah, okay. I just repeated what I said. Yeah. Okay. This one is the most exotic one. Stretch X to become length M, stretch Y to become length R, and then just stick Z at the end. I know you can talk about doing this a lot more, but it just doesn't come up for what my purposes. All right. Uh, we now apply the proposition we're reversing, from which we will eventually derive con S or P, namely this, right? And we apply A to our G. I think we already did this. Um, Now we'd have to make this definition. We have to take pieces of this invariant maximal clique S. You have to take pieces of it. The set of all X such that when you extend X, you get S. In other words, it's the set of all, let's say, 5 tuples, such that if you repeat the last term, K12 minus 5 times, you get something that's in S. That's a smaller, the dimensional restriction on S, okay? And then we have the following. Vertices outside S are exactly the vertices blocked by a vertex in S or block some vertex in S. That's trivial. If X blocks Y, then there's a lot of repetition in here, which is all right. The abnormal vertices outside S are exactly the abnormal vertices that are blocked because it can't block. All blockers of abnormals have strictly lower max from stipulations. All blockers of normals have strictly lower max from stipulation. There's no blockers of strays. Now, this is important. If max of X is 1, special things happen. And X is not exceptional, then X is not in S if and only if it's blocked by a vertex in S, because it can't block anything. If it's not exceptional, it can't block anything because you have to raise the max in order to block something. You have to raise the max, but the max is already 1, the right endpoint. And if X is not an S, all blockers of X have strictly lower max. Yeah. Well, we talked about it before. If any two exceptional elements of the same largest and second largest terms are equal. Okay, largest and second largest are equal. That's just from before. And any two exceptional elements of S with the same terms after their first term are equal. Because they're in the clique. Otherwise, they'd block. Okay. Now, for the reversal, we'll be using the condition max X equals 1 extensively, heavily exploiting this thing up here, heavily exploiting this. This is how we rely heavily on the right endpoint of Q minus 1, 1. From section 3, we cite only normal declared sets. From section 4.4, we cite some normal and some abnormal declared sets. In section 4.5, we cite some normal abnormal declared sets as well as the unique exceptional declared set, because that's used, these exceptional things are used in order for us to do tupling. All declared blockers will get used in sections 4.3 to 4.5. And now we have the following table, which may be useful. We have the table here. Normals can block normals. Normals can block abnormals. Normals can block exceptionals. Normals can't block strays. Abnormals cannot block normals. Abnormals can't block abnormals. Abnormals can't block exceptionals and abnormals can't block straights. Exceptionals can block normals, don't necessarily have to. Exceptionals can block abnormals. Exceptionals can block exceptionals, and exceptionals can block strays. Uh, Strays can block normals. Strays can block abnormals. Cannot block exceptionals, and strays can't block strays. These are all from what I said earlier. And also, it's only less than or equals, except that when you have we have normal blocking. Oh, I'm sorry. I'm sorry. Normals, you have strictly lower max when a normal blocks. You have strictly lower max when a normal blocks. Yeah. And when a normal gets blocked, you have strictly lower max. The equals comes up only here with the exceptionals. They can compete like that. All right. Now I'm almost done today. I've got one thing that's important. Um, Notice this is trivial. This is part of our setup. X is not in S if and only if X is blocked or blocks a tuple. So if you're outside the maximal clique, you either are blocked or you block. Okay, that's the way it's set up. However, I'd like to know that if X is not in S, then X is blocked by a tuple in S. That would be great, very convenient to know that if X is outside S, then it's actually blocked. Because the blockers are lower and, this becomes more like a kind of transfine induction, which is much easier than what I'm doing. So, but that only happens for certain X. And we now develop a sufficient condition for this to hold. This is this thing that I took from section 6 and I stuck it in the earlier sections. From the bookkeeping section, and I stuck it in earlier sections. So we need a lemma, purely combinatorial. Suppose X and the ith iterate of J. So J is this, this thing I'm invariably spec to, right? Uh, the whole thing based on J, right? J invariance. J to the I means the ith composite. So if Y and J, Y, I, Y are both in D union singleton 1 to the K12. Remember, D is the domain of J, actually. Yeah. Then X, J, I, Y is order equivalent to some X prime Y. In other words, I've lifted up Y many steps, say, by this J, and I got another vector, another tuple sitting around. May not actually be in here, may not actually be very nice. Then I can push this down. I can push this down to here. I can push JIY back down to Y and push X down somewhat to X prime. And this is proved by partitioning X to A less than B less than C, where A is the negative part of X, B is the non-negative part of X, strictly below the non-negative part of JIY, and C is the remainder of X. So we've got this on top, this, and this, A, B, and C. And I can define X prime as follows. I subtract C by the number I, subtraction, and that's going to be fine. This JI already assumed to make sense. Yeah, we can subtract I. This remains all non-negative. And then we map B, the middle section of X, order preserving onto Q minus 1, 0, staying greater than all negative terms of X and Y. Okay. Just stick it in that gap between the negative stuff in X and Y and 0, and don't change A at all, the negative part of X. And now it's clear that X, J, I, Y is order equivalent to X prime Y. All right. So now we have the last thing I want to say, which is this. So suppose I have y in D union singleton 1 to the K12 that's normal or abnormal, and the max is greater or equal to 0. If y is not in S, then y has a blocker and would have to be with strictly lower max, because that follows from the fact that y is normal or abnormal. Okay. Let y be as given, let y be not in S. Y has a blocker or y blocks X in S. Y has a blocker or y blocks some X and S. Okay, fine. Uh, y blocks some element of S. I'm not going to really use that letter, element of S. If y is abnormal, um, then we're done because abnormals uh, don't block, so they have to have a blocker. So we assume that y is normal. So let I be unique such that jiy has max 1. Could be y could be 0. We just take the largest term in y because remember it's in here. And y has a positive, a non-negative, y has a non-negative coordinate. Yeah. So we know that we can push it up so that it now has max 1. And this, yeah. Um, then ji of y is normal because it started off normal, and ji of y is not an S. So by the theorem we talked about earlier, jiy has to have a blocker X because the max is 1 and it's normal. Okay, we had that before, and by that, and then by lemma 425 that we just proved the combinatorial lemma, xjiy is order equivalent to x prime y for some x prime, right? That's what theorem 425 said, lemma 425. Right? We get some x prime y. Then uh, yeah, then x prime is a blocker of y because the blocker relation is order invariant, right? Since y is normal, we also have this because uh, when you block a normal thing, you have lower max. Okay? Yeah. So this theorem here is a major tool used in these sections and elsewhere to establish various equivalences of membership in S. I used to say C section 6 all the time. Remember when we did this, C section 4.6 all the time. I used to say that. Now we don't have to see. The only thing we have to do is C4 section 4.6 from for the definition of G, for the definition of G. And we reason using this. You see, we reason using this because that's the situation we're going to be in when we're looking for blockers. See, we're in a lot of these in section 4.3 to 4.5, we are looking for blockers. I always are looking for blockers. I want to argue that these don't block anything. Or if they do, it's not that they don't block anything because they're lower than 1. It's just that they always have a blocker because of this theorem. All right, so that's my final lecture on that actually does the reversal. Now, next week, I want to talk about what base theory is this reversal taking place in, and what base theory could it take place in. It actually takes place in not quite WKL naught, not quite ACA, even ACA naught. It takes place in ACA prime, which is an extension of arithmetic comprehension, which allows indefinite numbers of jumps. For every x and for every n, there's internal n, there's x to the n exists. So it's some sort of arithmetic comprehension, this whole thing can be reversed. Then I show next time that first thing I do is show that without much change, just some commentary, you can put it in, you can get it in WKL naught. And then with some additional work, heavily relying on something that is credited to Leo Harrington, we can reduce this to RCA naught. So the reversal can be done in RCA naught. And then I want to talk about some other things too, namely that that as the dimension grow, that there's a dimension such that this statement that we're reversing, the statement that we're reversing, as the dimension goes up, the logical strength goes up through SRP. Big open question, of course, is any more precise information. For example, how many dimensions do I need in this statement so it's not provable in ZFC? This is unclear and requires serious serious adaptation of the ideas in this reversal, because as you might expect and saw, I was not sensitive to the dimension I was using. It was just that it was finite. Okay, Andreas, I'm done now.